Lesson 18.2, Stretching, Compressing, and Reflecting Tangent Graphs. What are the key features of the graph of the tangent function? Well, let's see. It has a period of pi, a period of pi, a vertical asymptote at x equals pi over 2 plus n pi, where n is an integer. And let's see here. X-intercepts at at n pi, where n is an integer as well. Graphing the basic tangent function and its reciprocal. Recall that the tangent of an angle can be found from the relationship tangent theta equals sine theta divided by cosine theta. Using the coordinates of the position of the unit circle, xy equals cosine theta sine theta, the value of the tangent function can also be found from the ratio of y to x. The tangent of an angle is undefined when the denominator of the defining ratio is 0. As theta increases from 0, the first angle in radians at which the tangent becomes undefined is, and if you start here at 0, the first place that'll be undefined is right here, right there. And that's because that's 0, 1, right? So it becomes undefined at pi over 2. As theta decreases from 0, the first angle in radians at which the tangent becomes undefined is, so we start here at 0 and decreases. The first place would be right here. And that's at 0, negative 1. So that's negative pi over 2. Or 3 pi over 2. If you go this way here, that would be 3 pi over 2. All right. The tangent is undefined. The tangent is defined between these two angles, so it's only defined from here to here. Use special triangles and xy coordinates of the unit circle to fill in the table of reference points, the x-intercept and the halfway points. So tangent theta at negative pi over 4, and let's try that. Tangent theta at negative pi divide 4, and that gives you negative 1. So here, negative 1, tangent 0 would be just 0, and at pi over 4, it will be 1. Use your calculator to evaluate the tangent as it approaches pi over 2, which is 1.5708, and negative pi over 2, which is negative 1.578. So tangent 1.492, let's see, tangent 1.492, and that gives you 12.66. So we'll put 12.66 in there. And then if you put 1.555, that'll give you 63.30. And if you put in 1.569, that will give you 556.69. All right, what about the opposite, the negative? So let's see here. Let's go up here and grab that. And we'll make it negative. And that'll give you negative 12.66. So that's negative 12.66. And again, this would be negative 63.30 and negative 556.69. Okay. The tangent function decreases or increases without bound as the angle approaches pi over 2 from below, and decreases without bound as it approaches negative pi over 2 from above. There are vertical asymptotes at pi over 2 and negative pi over 2. So we're going to use the reference points from step A and the asymptotic behavior observed in step B to graph f of theta equals tangent theta from negative pi over 2 to pi over 2. Now on the last page, we learned that there were vertical asymptotes at negative pi over 2. So we'll put one right there. And pi over 2. And that's kind of crooked. Yeah, that's a little bit straighter. All right. Draw the vertical asymptote. We did. Continue to graph f of theta equals tangent theta from pi over 2 to, well, let's see. What did we miss? The little table that we did. We had at pi over 4, it was 1. At 0, it was 0. And at negative pi over 4, it was negative 1. So that's right there. Let's draw that in. Okay. It says continue the graph from pi over 2 to 3 pi over 2. So, and again, we have reference points here, here, and here. And that's going to be 5 pi over 4, and that's going to be 3/4 pi. And let's see here. Draw. Yeah, let's do another. Again, we got reference points here, here, and here. It gets real close to it, but it doesn't actually touch it. And then we got another one right there. And again, we got reference points here, here, and here. And we got a reference point here. And we got a reference point there. So. And it also goes to the left here. It goes to the left, so this is pi, so that's going to be 3 pi over 2. And we got reference points here, here, and here. It's supposed to be right there. And let's see, we got one here and one there. So it's going to go like, try that again. All right, so we graphed it. And 3 pi over 4 was, well, let's see, 3 pi over 4 was negative 1. Pi was 0, and 5 pi over 4 was 1. Use the same technique to graph from negative 2 pi to 4 pi, and we've already done all that. So that was E. F, the cotangent is the reciprocal of the tangent. It can be found by inverting the ratio used to find the tangent of an angle. So cotangent theta equals 1 over tangent theta, which would be cosine theta divided by sine theta, or x over y. Like the tangent function, the graph of cotangent has regular vertical asymptotes, but at angles where sine theta is equal to 0 instead of cosine theta. So where's sine theta equal to 0? I think it's at pi, and I think it's at multiples of pi. The first interval where the positive angle measure and define. Well, let's just draw one real quick. So let's put some. Let's draw. And let's see here. So where is sine theta equal to? So sine theta, this is 1, 0. So sine theta equals 0 there. And then over here, this is 0, 1. So sine theta is 1. Over here, this is negative 1, 0. So sine theta equals 0 here. Okay? So kind of like before. So you're going to have is bracketed the first interval with positive angle measure and define values of cotangent is bracketed by vertical asymptotes at theta equals 0 and theta equals pi. Okay? So cotangent theta at pi over 4 is going to equal 1. At pi over 2, it's going to equal 0. And at 3 pi over 4, it's going to equal negative 1. Okay? So, and with the tangent, we were just doing this side over here. With the cotangent, we're just doing this up here. Okay? We're just doing this up here. Okay. Cotangent is undefined everywhere tangent is equal to 0. And cotangent is equal to 1 or negative 1 when tangent is equal to 1 or negative 1 respectively. Okay. Sketch the asymptotes of 0 and pi and use the reference points to sketch the first cycle of f of theta equals cotangent theta. Then continue the graph to the left and to the right using the same pattern. Well, okay, the first one is going to be here at 0, right? Okay, we can just use y. The next one is going to be here at pi. And I want to use a broken line. We'll use it. Yeah, still a little low. All right. Now, what was it at pi over 4? At pi over 4, it was 1. So at pi over 4, that's going to be half of that. That's going to be right there. At pi over 2, it was 0. And at 3 pi over 4, it was negative 1. So it's going to graph something like this right here. Yeah, a little too sharp of a curve there. It's supposed to have been smoother. All right. And then the next one over, it'll go from pi to 2 pi. Okay, and we'll have a reference angle. This is pi over 4, so this is going to be 5 pi over 4. This is pi over 2, so add pi to that, and you're going to have 3 pi over 2. This is 3/4 pi. You're going to add pi to that, so you're going to have 7 7/4 pi, and then it goes. You see why they note the period? Because it's real easy. It repeats itself. So you just add pi to everything. So here we had 2 pi. We add pi. That gives us 3 pi. And then add pi to that, and that gives you 4 pi. Okay. And add pi to that, and that puts it right there. Add pi to that, and that puts it right there. Here, and here, and here, and here. And subtract pi. Subtract pi from that, negative pi. Subtract pi again, and another negative pi. So we're going to have here, 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 and here. And like that. All right. So there we go. Good deal. And that's what. And notice it just repeats. It repeats and repeats. Okay. Let's draw one in the old calculator here. Let's go to graph and tangent. And we have to use X. It doesn't have a theta button here. Tangent X. And you see what? And then the last one we just did was cotangent. So let's draw that real quick. Cotangent. And we'll put in X. And then it's just the opposite. Okay. Now I think we have to change the scale, but all right. So describe the behavior of the graph of the tangent function. Include where the function equals 0, where it has asymptotes, what the period is, and over what regions it is increasing or decreasing. So let's see here. Tangent theta, let's see, tangent theta equals 0 at integer multiples of pi. At integer multiples of pi. All right. Vertical asymptote at half odd. All right, at odd half integers. At odd half integers. Odd half integers. Multiple of pi, and has a period of pi, has a period of pi, and is increasing where defined. And let me go back and show you what I'm talking about. So tangent theta equals 0 at integer multiples of pi. So integer multiple. So at pi was 0, pi, 2 pi, 3 pi, negative pi, negative 2 pi. That's where it's going to equal 0. has vertical asymptotes at odd half integers. So here at odd half integers, pi over 2, 3 pi over 2, 5 pi over 2. See, that's 1 is odd, 3 is odd, 5 is odd, 7 is odd, -3 is odd. So odd half integers of pi has a period of pi. Notice from here to here is a pi, from here to here is a pi. It is increasing from left to right. It increases. Okay, it goes up. All right, good. Good. So that kind of explains what I was saying, because that can be, sound a little might be a little difficult to understand. The cotangent, so cotangent theta equals 0. And let's go, where does cotangent theta equal 0 at? Just past it, right there. It equals 0 at -3 pi over, at negative pi over, at pi over 2, at 3 pi over 2. It's where the other one had asymptotes, right? Okay. So we're going to say cotangent theta equals 0 at odd half integers INTEGE. I don't know why I keep putting that R there. Integers at odd half integer multiples of pi. Okay, and let's see, where's the vertical asymptotes at? Well, the vertical asymptotes, negative pi, 0, pi, 2 pi, 3 pi. So it's going to have asymptotes. Let's see, vertical asymptotes at integer multiples of pi. And it is, well, it has a period of pi as well. Pi. I was about to spell pi. And it is decreasing where defined. Okay, good. Use reference angles to explain why the graph of f of theta equals tangent theta appears to show that f of negative theta equals negative tangent theta. Okay, the reference angle for an angle negative theta in quad 4 is the angle theta in quad 1, and the sine of the tangent of negative theta is the opposite of the sine of the tangent of theta. The reference angle for an angle negative theta in quad 3 is the same as the angle theta in quad 2, pi minus theta, with the opposite signs for the tangent function. Let's see here. Let's just draw one real quick and let me show you. Okay, let's see here. We'll draw one real quick right here. And let's draw something so we know what we're talking about. Okay. All right. Here in quadrant 1, here in this quadrant 2, quadrant 3, quadrant 4. All right. Sine and cosine both are positive here, so that's positive, positive. So tangent is going to be positive because tangent is sine divided by cosine. Over here in quadrant 3, they're both negative, right? Cosine is negative and sine is negative. So tangent, again, is going to be positive. Okay? Up here, you're going to have negative cosine and positive sine. So what happens when you have a positive divided by a negative? That's going to give you a negative theta. Okay, and over here you're going to have positive negative. Okay, what happens when you have a negative divided by a positive? You get a negative result. Okay, so use reference angles as why the graph of f theta equals tangent appears to show that. Okay, that's why right there. These two right here. Graphing f of x equals a times tangent 1 over bx. The tangent function can be graphed on the xy coordinate plane by letting x represent the angle in radians and y represent the value of the function. The plot of a transformed tangent function can be found from the transformation parameters, as you have done for other families of functions. The parameter a causes the graph to stretch for alpha, for the absolute value of a is greater than 1, and compress for the absolute value of a is less than 1, and or reflect across the x-axis for a is less than 0. The parameter b controls the horizontal stretches and compressions of the function and the location of the vertical asymptotes. With the asymptotes x equals negative pi over 2 and x equals pi over 2 moving in or out to x equals negative b pi over 2 and x equals b pi over 2. Use the asymptotes to guide your sketch by keeping the curve or curves as drawing more than one cycle inside the asymptotes. The other guide to the shape comes from halfway points at negative pi b over 4 negative a and pi b over 4 a, which correspond to the points negative pi over 4 negative 1 and pi over 4 1 in the parent function. So plot one cycle of the transformed tangent function g of x on the axes provided with the parent function f of x equals tangent x. Okay, so you can do a by yourself, and when you come back, we'll do b together. So g of x equals negative 2 tangent 2x. So a is going to be negative 2. Well, what is b? Remember, b is supposed to be 1 over b equals, and that would be 2. So multiply both sides by 2, and you get 1 equals 2b. Divide both sides by 2, you get 1/2 equals b. So b is going to be 1/2. Okay. Draw the vertical asymptotes at x equals. The asymptotes, remember, let's see, x equals, and that's going to be plus or minus pi b over 2, right? Well, what is b? b is 1/2, so that's going to be plus or minus pi 1/2 over 2, which is plus or minus pi over 4. Okay, 1/2 divided by 2 is 1/4. So we're going to have vertical asymptotes at we're going to have vertical asymptotes at let's see, negative pi over 4 and pi over 4. Okay, so let's draw those real quick. And let's see, about right there. Not too shabby. And then another one right, a little bit too far. Still a little bit too far. Okay, let me clean that up a little bit. So there's our vertical asymptotes. Here and here. Draw the reference points at, well, how do we get the reference points? Remember, the reference points are negative. Let's see here. Let me do that in this color here. Reference points are going to be negative pi b over 4, negative a, and they're going to be pi b over 4a. Okay, so what is b? So let's see here. We got negative pi, and b is going to be 1/2. So we got 1/2 over 4, and then negative 2, or negative a, that's going to be negative 2. So this is going to be negative pi over 8, 2. So we're going to have negative pi over 8, negative pi over 8, 2. That's going to be right up there. Okay. And then we got 0, 0. And then we'll just change the signs on this right here. So that would be positive, and that would be negative. So that's going to be pi over 8, negative 2. Pi over 8, negative 2 is going to be pi over 8, negative 2 is going to be right there. So it's going to look like this. So can you see the vertical stretch now? It has taken the curve from this right here. It's taken the curve from this right there to that right there. It stretched it out by a factor of 2. And then that was the vertical stretch, and the horizontal compression by 1/2. So it went out here, and it just cut it in half. All right. Why is the vertical stretch parameter A referred to as the amplitude when transforming sine and cosine functions, but not tangent functions? If it is not the amplitude, how can it be used to help graph the function? Well, on sine and cosine, they're limited, right? Well, tangent is it goes to infinity, right? Up like that. It goes to infinity. So the amplitude of a periodic function is the distance from the midline to the maximum minimum, like on the sine or cosine. But the tangent doesn't have a max or a minimum. The points of the graph halfway between the x-intercepts and the asymptotes have a vertical position of a or negative a. So let's see here. How does it help? How does the amplitude help? Well, it gives you, and what was that? Negative pi over b 4. It gives you the y value, and then pi b over 4a. So it gives you the y value, and what it does is it just shows you, like, you've got a curve that goes like this, and it stretches that curve out to and I'm still not drawing it real well, so it stretches that curve out. So that's what it does. It stretches that curve out. All right. Make a conjecture. Do transform functions of the form f of x equals a tangent 1 over bx have the same behavior seen in the parent function? That is, f of negative x equals negative f of x. Explain your answer and how it helps to graph the transform function. All right. F of negative x equals, what does it do? Well, the negative transforms. Well, let's see. How about reflects? Reflects the graph over the x-axis. Okay. let's see, f of negative x equals a times tangent, and that would be negative x over b, which that will equal negative a tangent x over b, which is negative f of x. Okay, and we could try that. Let's try that. Let's see here. On new document, no, and then graph, and we'll put, let's see, 2 tangent x. Okay, now let's put in 2 tangent, and we'll put in negative x. So in other words, our b is 1. Let's see, negative x. Let's see how that works. Aha. Well, okay, so that's 2 tangent negative x. What if we tried negative 2 tangent x? And if it does right on top of the red, we're good to go. And it did. Okay, so that's what we're trying to show. All right, graph g of x equals negative 3 tangent x over 2. So what is a? A is negative 3. What is b? Well, let's see. 1 over b equals 1 over 2. So b equals 2. All right. So we're going to have vertical asymptotes. Vertical asymptotes. Where's the? Well, we've got it here at negative pi over 2 and pi over 2. Well, what is this b going to do? What is this b going to do? So we're going to have, let's see, we're going to have x equals plus or minus, that's plus or minus, pi, and then b is 2 pi over 2, right? 2 pi over 2. Well, these 2's are going to cancel out, so we're going to have plus or minus pi. Okay? So let's draw our asymptotes at plus or minus pi. It's halfway between those two. That still looks a little crooked. All right, so there it is. There's our vertical asymptotes. Now, what about our reference points? What about our reference points? Reference points. Let's try a different color. Reference points. So our reference points are going to be, let's negative pi b over 4, and then negative a. And so that's going to become negative pi. B is 2, so we got 2 over 4, and then negative 2, which is negative, well, that's a 2, that's a 1, so that's going to be negative pi over 2 and negative 2, right? All right, so we have, let's go right here, pi b over 4 and a. So that's going to become pi times 2 over 4, and then, of course, negative 2, right? And so those cancel out 1 and 2, and that gives us pi over 2 negative 2. So let's pi over 2, and then pi over 2. Well, that was supposed to have been a, and I don't know why I put a negative there. It should have been positive. All right, so pi over 2. Well, a was negative 3. So why did I put 2 there? So negative, negative, negative 3. That's going to give you positive 3. I did that from the other problem, and that's going to be negative 3, negative 3, and that's going to stay negative 3. So negative pi over 2, 3, that's going to be right there, 0, 0, and negative 3 here. And then see how it stretched up that curve? All right, good. Writing f of x equals a tangent 1 over bx. To write the function rule for a graph of a transformed tangent function, identify the value of b from the spacing between the asymptotes. The asymptotes spread apart by a factor of the absolute value of b if the absolute value of b is greater than 1, or move inward if the absolute value of b is less than 1. The asymptotes are the points where the function is undefined, or x over b equals pi over 2 plus n pi, where n is an integer. The separation between any two consecutive asymptotes is b pi. The parameter a can be found by evaluating tangent b over x at a known point. Finally, unless degrees are specified, the input to the tangent function should be assumed to be in radians, even if the x-axis of the graph is labeled with integers instead of multiples of pi. Write the function rule for the transformed tangent function of the form f of x equals a tangent 1 over b of x from the graph. So go ahead and you take a look at a, and when you get back, we'll do b together. All right. Find b from the distance between the asymptotes. So we have an asymptote at negative 3 pi over 2. Negative 3 pi over 2 minus, and then we have another one at 3 pi over 2. Okay, so that will equal negative 3 minus 3. That would be negative 6 pi over 2, which is negative 3. Let's see, negative 3, which equals negative 3 pi. All right, so if we divide both sides by pi, we get, and one, those are negatives, negative. So b is going to be negative 3. Negative 3. Well, it's actually going to be just 3, because we could have done, that's pi minus negative 3 pi. Let's do it like that, because that's always going to, anyway. So we'll do it that way there. All right, so we got b equals 3. Okay, good. Substitute the value of b. So you got a tangent, and then you got 3x, right? Well, it's not 3x, because remember, it's 1 over bx. So that's going to be 1/3 x. All right. Use the point 3 pi over 4, negative 2 to find a. So we're going to put negative 2, a tangent, 1/3, and then 3 pi over 4. Okay, so if we cancel those out, you get pi over 4. All right, well, what is tangent pi over 4? And let's try that in our calculator. tangent, let's see here, tangent pi or x divide 4. It's not x, it's pi. Pi divide 4. That's 1. So tangent pi over 4 equals 1. So a is going to equal -2. Write the function rule. So if a is -2, let's put -2 in there. Tangent 3, or I don't know why I put 3. That's x over 3. Okay, good. Now let's see. Your turn. Write the function rule. Write the function rule for the transform tangent function from its graph. Okay, so what do we know here? We know. Let's see here. We have some asymptotes. Let's see. That's -1. So it's -3/4, -1/2, 1/4. It goes from 1/4 to 1/4, right? So this is -1/4, and this is 1/4. So pi b equals, and that's going to be 1/4 minus -1/4. Okay, 1/4 minus -1/4, and that's going to give you 1/4 plus 1/4. That's going to be 1/2, right? So pi b equals 1/2, and then let's divide both sides by pi. Okay, so b equals 1/2 pi, 1 over 2 pi. One over 2 pi. So that's what b equals. All right. 1 over 2 pi. So now let's see here. What do we got? A tangent 2 pi, and then that's going to be 1/8 equals 1/2. So that's going to become a 1. That's going to become a 4. 4. So you got a tangent 1/4 equals 1/2. Well, we know tangent, and I dropped the pi off of there. That's pi over 4. We know that's 1, so a equals 1/2. 1/2. So f of x equals a, which is 1/2, tangent 2 pi x. Okay, there we go. So that's what that was all about. 1 over 2 pi. Okay, good. Comparing tangent functions. To compare tangent functions, such as, to compare tangent functions expressed in different forms, such as graphs, tables, and equations, find the common elements that can be determined from each. Asymptotes are generally easy to recognize and can be used to determine the period of the function. Compare the two tangent functions indicated by comparing their periods. All right, so I'll let you do A by yourself, read through A, and then when you get back, we'll do B together. All right, so f of x is shown in the graph. G of x is shown in the table. Okay. All right. So negative pi over 4 is undefined. Negative pi over 8. Negative pi over 8 is negative 1. 0, 0. Okay, good. So what do we got here? What do we got? The period of f of x equals, well, that's going to be pi over 4 minus negative pi over 4. Okay, and 1/4 plus 1/4 is 1/2, so that's going to be pi over 2. The asymptotes of g of x can be found where the function is undefined. And so that was this one here and this one here. Now, the period of g of x is pi over 4, minus negative pi over 4, which is pi over 2. G of x has the same period as f of x. Not too shabby. Now let's try your term. F of x equals 3 tangent pi over 3x. Okay. So, what do we know? F of x, b equals 3 over pi. Okay, and the period equals, and then it's pi times the absolute value of b, which is pi times the absolute value of 3 over pi, which is just 3. The pi's will cancel out. So that's going to give you 3. G of x has asymptotes at, negative 1 over 6 and 1 over 6. Right? So its period will be 1, 6 minus negative 1, 6, right? Which equals 1/3. So the period of, g of x is less than the period of f of x. All right. Modeling with tangent functions. Tangent functions can be used to model real-world situations that relate perpendicular measures, such as horizontal distance and height, to a changing angle. Example 4. Read the description and use a tangent function to model the quantities. Use a calculator to make a table of points and graph the model. Describe the significance of the asymptotes and determine the domain over which the model works. Well, let's see here. A climber is ascending the face of a 500-foot high vertical cliff at 5 feet per minute. Her partner is observing from 150 feet away. Find the function that describes the amount of time climbing as a function of the angle of elevation of the observer's line of sight to the climber. Does the viewing angle ever reach 75 degrees? Okay. The distance from the observer to the cliff base is 150 feet. The cliff is 500 feet high. The climber is climbing at 5 feet per minute. Formulate a plan. A vertical line from the cliff base to the climber forms a second leg of a right triangle that can be used to find the appropriate trigonometric ratio. Use the right triangle to find a relationship between the height of the climber and the angle of elevation from which the observer is viewing. To find the time as a function of the angle, use the speed of the climber to rewrite the tangent expression. The height as a function of viewing angle is tangent theta equals, and that would be the height over 150 feet. The height of the climber is a function of time. H equals and 5 feet a minute, right? Something like that. 5 feet. Substituting 5t for h in the second equation gives tangent theta equals 5t over 150. So t is 30, t over 30. So t, and then if you multiply both sides and divide by, so t, multiply both sides by 30, you get 30 tangent theta, right? Okay. So if we put that in our calculator, so, and then let's see, tangent 0. That's going to give you 0. All right, 0. Now, these are degrees. Make sure you put degrees in your calculator. So let's see here. Tangent 15 degrees. That's, what do we got here? What's my 7, 2 radian? All right. Oh, you know what I didn't do? Dadgum you. 30 tangent. That gives you 8.03. 8.04 when you round. And then let's go up there and grab it again. And let's put in 30 this time. $17.32. And then you put in 45, and that gives you 30. And you put in 60, and that gives you 51.96. Okay. Using the function to calculate time, a viewing angle of 75 degrees should be reached in, and that would be 111.96 minutes. However, the height at that time would be 559.6 feet, which is higher than the cliff top. This means that the viewing angle of 75 degrees is impossible. All right, let's take a look at this next one here. You observe a model rocket launch from 20 feet away. Find the rule for the rocket's elevation as a function of the elevation angle and graph it. Okay, you observe, so we're going to have h over 20 equals tangent theta, the height over 20. So h equals 20 tangent theta, right? Okay, so height and then elevation. And let's draw here. So 0 gives you 0. And then, let's see, 15, 30, 45, 60, and 75. Okay, so 20 tangent 15. Let's see, 20 tangent 15 degrees. And that's going to be 5.36. 5.36. And if you put the rest in your calculator, 30 would give you 11.55. 45 would give you 20. 60 would give you 34.64. And 75 would give you 74.64. Okay, so we got 0. 15, that's halfway in between here, would be 5 point, and we'll say it's about right there. 30 would be here. That's going to be 11.55. 45 would be 20. 60 would be 34. Let's see that. 60, that's 34, would be about right there, maybe halfway. And then 75 would be 74. It's going to be right up there. So it's going to look like this. And it should look something about like that. Not too bad. Elaborate. If sine, cosine, and tangent are all based on coordinates of the unit circle, why do sine and cosine have a domain of all real numbers while the tangent function does not? Sine and cosine correspond to the coordinates of the unit circle directly, which have value for all angles. Because tangent is a ratio of coordinates, it can become undefined whenever the denominator is 0. So let's see, sine and cosine. And I misspelled correspond. Correspond to the coordinates on the unit circle directly. Which have value for all angles. Okay. Tangent is a ratio of coordinates. It can become undefined whenever the denominator is 0. All right. Why does the tangent function have a different period than sine and cosine functions if they are all defined using the unit circle? The tangent function repeats itself as the angle moves through the entire unit circle. So it has 2 periods for every 1 period of the sine and cosine function. Let's see here. The tangent function All right, good. And you know, it goes, the circle does like this. So here's one period, there's the other period. Okay. Essential question check-in. How do the asymptotes and the x-intercepts help in graphing the tangent function and its transformations? Well, there are repeating vertical asymptotes whose spacing comes from the horizontal stretch parameter b. These guide the sketch of the curve because the curve will approach the asymptote but not cross it. The x-intercepts occur at regular intervals n pi b, where n is an integer. So let's see here. There are repeating vertical asymptotes. There are repeating vertical asymptotes. Whose spacing comes from the horizontal stretch parameter b. These guide the sketch of the curve because the curve will approach that's ch. Approach the asymptote but not cross it. The x-intercepts occur at regular intervals. And that they're n pi b, where n is an integer. All right, folks, great lesson. Great lesson. I'll see you tomorrow in class and have a good evening.